What we're going to look at in this video is one of the key topics that comes up when we do higher level mathematics, and that's the topic of differentiation. Now this is a new concept introduced at this level, so it makes sense to get our head around the idea of what it means and some of the basics of it before we really delve deeply into the applications of it and using it for things like optimization. Now think back to when we did straight lines. When we did straight lines, we were able to calculate the gradient of a line, which meant the steepness of it. However, this was for just straight lines. What we're able to do is we need to start to think about how we can look at the steepness or the gradient of other curves. So for example, if I was to draw a curve like this, let's say y equals f of x, and I gave you a point A here. Now at this point A, to calculate it, we would simply calculate f of A. Imagine I wanted to know the gradient of this curve. Now it's a curved shape rather than a straight line. So I can't just pick 2 points and do it the way we would a straight line. However, I can estimate it if I do that. So imagine I take another point here. I go along the x-axis. Let's say I go along the x-axis by a value of h, a plus h. I know that if I was to do that and I was to calculate the y part, I would simply do f of a plus h. Now what I'm able to do at this stage is imagine drawing a straight line going between the pair of them. If I was to calculate the gradient of that straight line, let's say the chord A to B, if I was to calculate the gradient of this chord from A to B, I'd be able to estimate the gradient of that curve. I'd be able to estimate the gradient of the curve between those 2 points. So to do this, we would just use our standard gradient formula we did for straight lines. So we know the gradient of A to B is y2 minus y1 over x2 minus x1. So these are the y values of the coordinates, these are the x. So it would be y2, so f of a plus h, minus y1, minus f of a, over x2 minus x1, so over a plus h, take away the value of a. So what that would give me is f of a plus h, take away f of a, divided by h, because the a's on the bottom would cancel here. So this would give me an estimate for the gradient here. But the issue is there's quite a big difference between this straight line and the curve. So you've got to ask yourself, how can I make that more accurate? Well, if I wanted to make that more accurate, I could pick a smaller value of h. So imagine I then picked the value of h to be there. So there would be my new a plus h. Well, the gradient of this line here would be different from the gradient there, but it would be a much closer estimation. If I wanted to keep improving this and keep getting closer and closer, ideal scenario would be that the value of h would go closer to 0, i.e. we'd get nothing in terms of what we're adding, so we would be able to get a much better gradient. Well, this allows me to use this as a generalization. So what I'm able to do is if I was to use the notation f dashed of a, and I was to say that that was to be the steepness or the gradient of my curve, I could say then that f dashed of a equals the limit as h tends towards 0, because ideally, like I say, that's the value we want for h, of the f of a plus h minus f of a divided by h. Now I can't just instantly substitute in the value of h equal to 0 in this. I've got h on the bottom. I'd be dividing by 0 mathematically. It's impossible. But this formula here allows me to be able to do it when I know the forms of f, when I calculate it at f of a plus h and f of a, when I know it at 2 separate values. This right here is a limit formula for what's called the derivative. So this is what the derivative is in terms of a limit formula when we're working at higher. Now, using this isn't something we'll have to do very often at this level. We'll have to know it, and we'll have to make sure we can occasionally use it, but this isn't the key thing for the derivatives we want. We want to be able to calculate the derivative of terms and equations when we're given. So what we need to be able to do in terms of doing that is know some of the general ways to get the derivative. Now imagine I told you I had something of a form f of x equals x to the power of n. So something to a power, x squared, x cubed, x to the power 900. I can calculate the derivative of that, f dashed of x, simply following the formula n x to the n minus 1. So bring the power down, reduce the power by 1. If I do that, I've got the derivative of anything written in this form, x to the n. And I can similarly do it if I've got a coefficient. So imagine I said to you I had f of x equals a x to the n. A is just a coefficient, it's just some random number. What I'd be able to do is take the derivative using the same form. The only difference being is that I have an a times n x to the n minus 1. When I did it, this would be the only additional part, this a value in front of this here. It's actually quite a straightforward thing to do and a straightforward thing to use. Now 9 times out of 10, this is what we're going to do when we're noting it. However, we do also sometimes get it when it's written as y equals x to the n, or y equals ax to the n. When we're doing that, our derivative takes a slightly different form when we do it. It actually takes the form dy by dx. However, that's the only thing that changes. The general form, these, stay the same. So if it was x to the n, it would still be n x to the n minus 1. And if it was ax to the n, it would still be an x to the n minus 1. All that changes is this part of the notation here. And this literally means the derivative of y with respect to x. Same as these sorts of things here. Let's look at a couple of examples of this and you'll see exactly how it comes out. So let's imagine I give you f of x equal to x squared. Well, to get the derivative of f of x when it's x squared, we follow the same routine we just talked about. Bring the power down, reduce the power by 1. So if I bring the power down, I get a 2x, and if I reduce the power by 1, 2 goes to 1. But remember, if we have a power of 1, we don't write it. So derivative of x squared is 2x. Job done. Similarly, if I had coefficients. So let's imagine I had 4x to the power of 7, and I wanted the derivative of that. Well, I'd do the exact same thing. I'd keep the number in front, 4. I'd then multiply it by the derivative of this part. So again, bring the power down, 7x, and then reduce the power by 1 to the power of 6. I would then just have to fix the coefficients at the front. So 4 times 7 is 28, and the x to the 6 would just remain the same. So I'd get 28 x to the 6 is my answer for that one. It's actually quite a straightforward process when we're looking at simple term differentiation. Even when we had something that was written in the form y equals, we'd still be able to do it that way. So let's imagine I had y equals 7x to the power of 4. I would still do it the exact same way, the only difference being, like we talked about on the previous slide, instead of f dashed of x, I'd write dy by dx. But my form would still stay the same and my steps would still stay the same. I'd still put my coefficient at the front, then I'd look at this part. Bring the power down, 4 in front, x, and then reduce the power by 1. Then simplify your numbers in front. So 7 4s are 28, so it's 28x cubed in this case. It's actually quite straightforward. One good thing as well is it allows us to do it if we have something reliant on a different term or a different letter. So let's imagine I gave you a function f of t, and let's say that was equal to 3t squared. All that's changed here is the letter we're using. So in these ones we used x, in this one I used t. The general form for the derivative stays the exact same. The only thing that changes is my final answer will have a t in it rather than an x. And we still approach it the same. F dash of t equals, put the coefficient in front, then multiply it by the derivative. So bring the power down, 2 times t, reduce the power by 1, well it'll be a 1 there. So we just leave it blank. Then we do 3 times 2, which is 6, and I get 6t. Job done. It doesn't change when the letter changes, it's just the final answer has a different variable in it and a different dependence. Differentiating terms on their own following these formats is quite straightforward, and it's actually a key skill we have to be able to do when we're working at higher. This is something we need to work on, so make sure that we can do this. Make sure that we know how to do simple single term differentiation before we move on to more complex scenarios.